Okay, let's wait some minutes for people connecting. For now, good evening or good afternoon, everyone, and thank you for being here. And I am Simone Serafini, marketing specialist for VIS Hydraulics and SmartFluidPower, and I'd like to welcome you to the first webinar in our series dedicated to dynamic simulation for fluid power. In our previous session, we showed how simulation can be integrated within a company, starting from a simple model. We also shared the implementation project carried out at the VIS Hydraulics Innovation Center, which is now fully embedded in the company design workflow. And if you want to revisit the previous webinar and explore the past session, as well as check out the upcoming events, you can using the link I will share in the chat. Today, we'll focus on energy and performance optimization of hydraulic components and systems, topics that are becoming increasingly critical in today's fluid power market. Our speaker today is Marco Rizzoli, one of the administrators of SmartFluidPower. Marco, over to you and enjoy the session, everyone.
Thank you, Simone. Welcome, everyone, and good afternoon. I don't know if we want to wait still 2 or 3 minutes before to start. But
okay.
Meanwhile, I can say that today we will start like in the previous meeting, in the previous webinar. We will start to observe, to analyze the output and the gain that we can obtain from OpenModelica software with our library from SmartFluidPower. So in the first 2 webinars of the series, we mostly shown how to use it, how it is its structure, and how to compose components and systems. But now with the previous meeting, we would like to show you the possible outputs that we can calculate, that we can use for the simulation for. I will move to the software right now, showing so that I will no longer show how to use it, how it is the windows and so on, but I will immediately move to a user case for this episode. We will analyze a system that is this one, is a system with power units and 3 different users. So we have 3 different loads. I think now we can start starting from to analyze the system. Starting from the power unit, we still have the electrical motor that is a source of rotational speed, but this time we are using a variable displacement pump. This variable displacement pump is 100 cubic centimeters displacement. And with a rotational speed of 1500, we are generating 150 liters per minute. The displacement of the pump is controlled by a load sensing system, an LS system. We have the compensator, the local compensator, the pump compensators here, with the piston that actuates the displacement of the pump. In the distribution, instead, we are having 3 different distributors that are 5 ports and 3 positions. Continuous position is not like discrete position, but we are able to move the distributor in order to control the velocity of the actuators, and this is the scope, the goal of the load sensing. The signal is connected to tank in neutral position, and instead it is connected to the load pressure when we are controlling the distributor. All three actuators are linear actuators that are 3 cylinders. The first one that is represented vertical, we are simulating no load, since we are not applying any load to the opposite side of the mass, but we are simulating the mass with inclination and the value of the mass to represent the gravitational load of the actuator. The cylinder number 2 and number 3 instead are equipped with logic to control and to define a specific cycle load for these actuations. So in this specific case, we are having a read of position of the mass or the actuator, and thanks to this table, we are able to define a personal cycle load. So we are, in function of the position, we are defining a force that is applied to the kinematic. In this case, is a resistive force. And this is the bottom line with the table function. On the top line, this counter is a simple logic that deactivate the force during the retraction phase. So, but anyway, it is possible to create a component with this logic inside and personalize the type of feedback we want to apply to the load. I mean, it is possible to define the load thanks to the velocity, to the position, to the inclination, and so on. So it is also possible to interchange this logic to define your personal cycle load. And what differs between the first actuator to the second and the third is that the first one only has gravitational load, but it is a huge cylinder. So we will see that it consumes a lot of flow rate and a lot of time to perform to perform its movement, while the other two are smaller but power loads, so power cycles. I mean, the resistive force will be much different to the previous one. Anyway, the pressure that the load generates during the movement, it is transmitted to the pilot line thanks to the shuttle valve, and will be connected to the compensator, the pump compensators. As you can see, in the model, there are every time a volume model placed between pumps and valves, just to underline that we need to follow our convention, that is resistive elements plus capacity elements, and so on. And this allowed the solver to elaborate the equations. The goal of today will be to analyze I mean, two mainly aspects from the simulation. We will analyze the cycle time plus the efficiency of the system. We know we are able to calculate the energy that the load requires to be moved. So we are able to calculate the energy consumed by the users, and we will calculate also the power generated by the electrical motor, or better, to be more precise, the power transmitted in the mechanical shaft. In this way, we can calculate the overall efficiency of this system dependent to the cycle we want to analyze. Of course, the efficiency of the system will be really dependent to the cycle. But if your case have different standard load cycles, it is possible to also to perform simulation in a batch of simulation, taking count all your standard cycles and see which is the best and which is the worst. Anyway, before to start the simulation, I will speak about the some very quick parameterization of the components and how to calculate the input power that we will look in the graphs after the simulation. The variable displacement pump, normally it is can be easily parameterized with the displacement of the pump and a constant parameter of mechanical and volumetric efficiency. But since this time we want to be more precise in this type of analysis, we can also activate the advanced model of efficiency in this type of element. Here, we are able to insert, to indicate in the parameter a map of efficiency for the pump. Specifically, a map in function of, so it is a table, a two-dimensional table in function of rotational speed of the shaft and the pump pressure. In function of these two variables, the model will evaluate this map of efficiency and use the real efficiency of the instant model inside of in the instant of the calculation. To elaborate this map of efficiency, it is possible to do it easily with Excel. For example, right now I'm using these tables, and with some dynamic formula, it is possible to compose the string that we need to insert here in the parameter to indicate the map we want to use. Also, if it is also possible to read the documentation about the pump, that helps you to understand how to use parameters. If you want to, I don't know, if you want to understand better how you can insert the efficiency map in the component, I suggest you to read the documentation of the element that, and also, and that helps you to understand how it behave and what you need to insert. But also, we have the documentation of the component, but we also are compiling and enriching the documentation online for the library, that we are like collecting the mainly questions, and we also have the chapter with the first model and helping you to compose the first model and to understand the rules and parameters and variables that we apply to this library. Okay, going back to the system, I will now show you how to insert a couple of lines in the code view to evaluate the power that we will absorb from the motor, the electrical motor. This is the code view. Everything you see right now, it is automatically generated by the software when you design our diagram with the library and the components. So this is all automatic composition. You don't need to know. But if you start to understand a bit of Modelica language, it is also possible to modify it. Right now, I need to evaluate the energy absorption at the inlet. So I will declare two variables. That is, the first one is the instantaneous power at the shaft, and the second one is the energy. To declare the variable, we offer some directory that is SmartFluidPower library .unit, and now we can declare, for example, power, this one, and I will call it input power. Okay. Also with the description. And the same for the energy. And I will call it energy in the system. Quindi this is the consumed energy by the system. Now that we declared two variables, we need also to define these variables. And we added two variables. We need to add two equations in our system. So we need to reach the equation section, and here we can indicate to OpenModelica how to calculate these two new variables. So the first one, that is power input, will be equal. Here we need to calculate the mechanical power at the shaft. So that is rotational speed multiplied by the torque. So we look inside the motor, and we know that for the velocity we need to see omega. That is also described here, angular velocity. But it is also shown in the documentation that omega is the variable that display the rotational speed of the motor, multiplied by the torque. And to find the torque, I need still to look inside the motor, .R1, that is the mechanical pin that connects the motor to the variable, to the pump, and R1 dot torque. And this variable is described in the general documentation of the mechanical library. We don't need to care about the units, since it is OpenModelica will care about the units. But since we define power and energy, OpenModelica will always calculate the equation in SI. So it will use watt and power, but we can change the units in the plot later on. About the energy, we should write something like energy consumed equals something, and we know that the energy is the integration of the power in time. There is no operator for the integral, but we have the operator for derivative. So it is we must to write power input is equal to the derivative of an energy input, like this one. And we must do this, but we don't need to care about what is defined and what is not, because OpenModelica is able to rearrange the equation and calculate by itself the unknown variable. In this case, it will use the first equation to evaluate the power, and it will rearrange the second equation to compute the energy. We added two variables and two equations. We can check that the system is solvable with this button here. We have 3,300 equations and the same number of variables, so it is possible to solve this problem, and we can run the first simulation. It will. I will show you later what is the cycle we are analyzing. I will start with the computation of the compilation of the model. I will show you the cycle we are analyzing with the animation of the library to understand if everything is behaving how we expect. And then we move to graph, and we will look to the performance of the power unit or the entire system. It is a 12-second simulation. We can look to here to the result. Okay, to show you the result, I will slow down the animation so I can describe you what is happening during the animation. Firstly, we start the simulation with the power unit under pressure and displacement that is 0 because of the pressure. We initially move the first distributor, and we goes to exit the first cylinder. As I said, this is a unload actuator that is just taking 6 bar of load while the pump is under 13 bar. But this is because of we just have a very big piston here that we need to exit and without a really a power consumption. Then we move in the second movement here. We are partializing the opening of the distributor since we want a speed control of this cylinder. You can look to the displacement of the pump that is regulating its displacement. Thanks to, I go back a while, thanks to the compensator, the flow compensator that is regulating the pressure at the actuator of the displacement. Then I will push distributor to the side to have the final movement at full speed with full displacement. And this is the second movement that we are evaluating in the cycle. After we move the third one, that is also this one is requiring 200, almost more than 200 bar at the pump, and at the end the power, the pressure compensator is stopping the displacement, the flow rate of the pump, since we reach the end stop and reach the max pressure in the system. To end the cycle, we will retract the second cylinder right now. This is the retraction phase, and we will stop this type of cycle. You can see that we are not showing any safety valve in the system, the actuator. We have no overcenter, no counterbalance or anti-cavitational valves, but this is just a performance analysis of the system. So we do not take care of have a full defined system. It is just we simplified the system. We want just to evaluate the performances, and maybe we could just insert a component that represent the drop of pressure of these elements along the power line, but we remove them for simplicity. Okay, now that the animation terminated, this is the cycle that we are analyzing. We can focus on some variable of interest, like about the pressure at the pump side and the load sensing pressure, for example, looking to P drop of the variable displacement pump and the pressure in the load sensing system. Here we can see that the load sensing is following the pump pressure, where we are controlling the speed of the cylinders. So in this phase, we are controlling the speed, and it is behaving correctly that the load sensing is following the pump pressure. More, I can show you, for example, the position of the piston, also the flow rate of the pump. Here I'm plotting in another variable. Okay, to have a comparison now. Okay, we have 3 lines that is not very readable, but for example, we are able to correlate pump pressure to the pump flow rate if we need to. It is possible to plot the position of the 3 cylinders, number 1, number 2, and number 3. We are able to see, for example, about the number 2, the change of velocity while we were controlling the speed, and the last phase where we command a full displacement, a full flow movement. And this is the third exit. Now we can plot the energy at the load. The energy at the load were defined by myself in the code here, but it is the same logic I show you for the inlet power. So I declare the power load and then the energy load. I can show these values about the power load 1, 2, and 3. And you can see that the first one almost is neglectable, the first power consumed by the movement of the first cylinder. And this is the instantaneous power consumed by the electrical motor. And to terminate, it is possible to, maybe I will show in Joule. Okay, 1, 2, and 3. This is and energy in. This is the energy, these were the energy, okay, these are the energy at the load, and the green one is the energy consumed by the pump. In the last one, the total efficiency is this one, that is the overall efficiency of the system along the cycle. And we reach a final value of 43% of efficiency. We were a bit higher, but you can see also here that we used some pump power, some pump energy to command the retraction of the actuator. And this, even if the actuator is unloaded, we consume energy from the pump. So this drops the efficiency of the system. But we reach the final value of 43%. Now, we have the efficiency of the system. The scope of today is to compare this system with a new one, that is this one. Our client asked to evaluate the new performance of the system that is equipped with prototype logic. We are equipping the system with a smaller displacement pump that is in this time is 66 cubic centimeter displacement. That is so we have a smaller pump with a bit higher efficiencies, and to help this pump, we are equipping the system with one accumulator and a block, a manifold that has a logic of charge and discharge of the accumulator. So the goal is to bypass the load sensing system only when we command the first actuator. We know that the first actuator is huge but do not consume power. So we want to increase the flow rate during the first cylinder exit. And this will bypass the load sensing system. So this charging block will receive the load sensing signal from the first cylinder and will activate or deactivate the accumulator. Inside, I can open this block to show you that inside we are controlling the accumulator with valves and logic of a piloting logic for this component. So we are controlling with logical elements and check valve. We are controlling the charge and the discharge of the accumulator. So also it is possible to combine the hydraulic library with the logic one in order to pilot and control the valving. And now we are able to re-simulate this new system and evaluate how it is behaving, if it does what we expect, and if the performance are getting better or worse. I will run this simulation right now. Okay, it takes a while. So right now with this new variable displacement pump, we are able to perform at least 100 liters per minute. The goal is to be shorter in time be more efficient in the system, and also have a solution that costs less, since thanks to the reduction of the variable displacement pump, we are able to compensate the expenses of the accumulator and its charging block. And maybe it is also possible to be cheaper in this solution. So we have these three aspects: the costs, the time, the cycle time, and the efficiency of the overall system. The cycle we are analyzing is the same of the previous, since we need to compare the same cycle load. We cannot change, or we would evaluate different things. And also one more thing, okay, I did not show you the specific of the oil, but it is an ISO VG 46, I think with 40 degrees, so almost cold oil in this case. And we can wait a bit to that it finished the evaluation. Okay, a quick look to the animation to check that everything is going well, is going as expected. I will go a bit faster, but okay, one important thing is the value that we start with the accumulator pre-charged, and we will finish the cycle with the same pressure in the accumulator, also to have a balance in the efficiency evaluation. Otherwise, we would stock energy inside the system without using it, and it compromises the efficiency. In the first exit, okay, I will slow down again. In the first exit, we will use the pressure of the accumulator, and here from the node, it is possible to see that we are using both pump and both accumulator flow rate to exit the first actuator. Then, while the other two cylinders are moved, the accumulator is switched off, is close to the system in order to keep active the load sensing system. We want that flow rate goes to the cylinder, not to fill the accumulator, even if the accumulator has a lower pressure. In the idle times, right? Okay, I will speed up. During idle time, I will use that idle time to fill the accumulator using the pump flow rate. That is, right now, I finish to exit all the cylinder, and with the pump, I fill the accumulator. That is, again, closed during the retraction of the cylinder. Before to stop the cycle, I will finish to fill the accumulator, and here we reach again the end of the cycle. Now everything goes as expected. I can move to analyze the directly. I think we can analyze directly the efficiency. And moving to here, total efficiency. It is the blue one. We were at higher efficiency, but then at the end of the cycle, we lost. We lost since we have a 42.3% of efficiency that is lower to the previous one. I do not, okay, but also we define inside the model, we define the volume of the accumulator and the target pressure for the accumulator charge. We also have here the gas pre-charge. We can play with these values and perform a simulation batch, a batch of simulation, and see if we can set up a system that really performs better. So it is possible, for example, to change the target pressure of the accumulator to 310 bar to increase a bit the pressure inside the accumulator, and reducing the volume of the accumulator to 5 liter. It was 10 liter. I forgot to tell you that was 10 liter accumulator. Now I move to 5 liter accumulator, and to run again to see if we are able. Meanwhile, I can also check the velocity of the first actuator, or also I can plot, for example, the pressure in the accumulator. Not now, during the simulation, I'm not able to plot variables. I need to wait the end, and then I can load the results. Here it is the accumulator. It will. Okay, now it is finishing. We are getting worse results, but probably I forgot something. This was a 50 liter accumulator. Let me check right here. 42 accumulator, then okay, here 5. I can run again. Anyway, I don't know if we have enough time. I will run the simulation and show the output of this new system. Meanwhile, I don't know if someone have some question that I can answer while we are waiting the end of the simulation. And after that, I think we can terminate the webinar. Okay. It is anyway. It is a 3,300 system equation, so it takes a while to compute and to resolve. Okay, I think it finished, and to end up with the webinar, I can just to show you that we reached a better efficiency in the system, reducing the size of the accumulator. And just to end up, also I can plot the velocity, the exiting of the first cylinder compared with, this is the okay, and this one, the blue one was the old one, and this is the new one, showing that also we are able to save some time, even if, but very little. It is 1 second. We are able to save 1 second over 12, reducing the size of the pump. And this is something that if you do not have simulation, you know only after the first prototype of the system. So this case, I think, really helps to have some estimation of your new design of the system. No question arrived, so I think that we can finish for today.
Okay, thank you, Marco, and thank you all for attending this session. I hope you find something interesting in this demonstration. Over the next few days, you will receive slides, recording, and a dedicated follow-up page for today's webinar. And for more specific requests or complex application use cases, you can also reach out to SmartFluidPower directly to our website or on LinkedIn. And we also invite you to complete the end of webinar questionnaire, which you can find in the chat. For us, this is a very important tool because it helps us better understand your needs and continuously improve our content. And by completing the questionnaire, you'll also gain access to the SmartFluidPower trial library and a dedicated free technical consultation focused on your specific use case. And of course, if you couldn't attend live, you're watching the recording data, you will also able to complete the questionnaire. We'll send you by email and receive all the materials. Finally, we'd like to remind you of the final session in our webinar series taking place on May 20, and it will be entirely dedicated to introducing simulation into company workflows. Don't miss it. So thank you again. Enjoy the rest of your day. I hope to see you at the next webinar.
Thank you for your participation.
Goodbye.